Good morning. Welcome to this master thesis presentation by Juan Pablo Rojas Martinez. The directors are Enrico Sergiacomi and Cristobal Lopez. The title is Lagrangian Studies in the Western Mediterranean Sea. So Yvonne, you have around 20 minutes, something like that, to present your work, and later, after this, we will ask some questions.
Okay, perfect. Thank you. So, hi, my name is Ivonne Rojas, and today I will talk about my project, my thesis, that are called Lagrangian Studies in the Western Mediterranean Sea. So, in this study, we're focused on a hotspot located at the north of Mallorca that cross many particles, and we will Lagrangian perspective. We study the principal sources of this particle that cross for that point. So to start with the talk, I want to start with the introduction and mention some of the general problem, also some important concepts that we have to take into consideration. The data description, what is our data set, also the methodology, how we compute the trajectories, show all the results, and finally the conclusions. So, well, what is the problem? Nowadays, we are aware that we are facing many environmental problems. This is because the plastic is one of the biggest causes of this. It's believed that near to 8 million of tons per year are thrown away into the ocean. So what happened with all the plastic that we throw away? So this plastic are carried by the ocean currents and will travel into the ocean. And there are some zones where the plastic get trapped. So, as for example, in the Great Pacific Garbage Patch, there is an island made of plastic that are located at the north of the Pacific Ocean. And well, this is damaging the ecosystem around it. So people are working on these issues, and they develop the Sustainable Development Goals that are focused on trying to solve all kinds of this problem. So what are we gonna do? Well, with Lagrangian studies, we will try to understand the pathway that follow, in this case, plastic, but also we can use for nutrients or other substances that are thrown into the ocean. So, well, this happened in the open ocean, but what happened in our sea, in the Mediterranean Sea? Well, we know that, well, there are some studies that show that in the Mediterranean Sea, most of the leaders are retained, but there are no specific area with show like a big concentration of this microplastic or the plastic. So what is happened? Due to the currents and the dynamics of the sea. So in this study, we focus only in the Western Mediterranean Sea. So I will explain the circulation in this part of the Mediterranean Sea. So we have 5 important zones that we can define. There are the first one, the Alboran Sea, that presents a big current that comes from the Atlantic Ocean, and for 2 big gyres, cyclonic and anticyclonic. And the second one is the Algerian Basin. In this part, we can find some eddies approach the 100 kilometers approach. The third one are the Balearic Sea, that is mainly consisting in the water around the Balearic Islands. That presents anticyclonic flow due to the strong currents that come from the north. Also, we can find the Lyon Gulf that is situated at the south of France, that has a current that goes a southwestward current. Last one, the Ligurian Sea, that has a strong current that goes to the Catalan Sea, Catalan coast, and is between Italy and Corsica. So we know like an idea of the description of the movement of this sea, but describe the trajectory of a particle in this system is not that simple. Why? Well, because the ocean is a complex system. And this occurs many processes, biological, physical, chemical, and also interaction with the atmosphere. And all these processes occur in different spatial and temporal scales. So we can find process in 1 millimeter, 10 kilometers, also in 1 second, 2 years. So try to set an appropriate scale is a difficult task. But what we can use to describe a particle or describe these dynamics? Well, we have 2 points of view, the Lagrangian description and the Eulerian description. In the Lagrangian description, we consider a motion like a particle, and we can use the Newton's laws, describe the position, the velocity. And in the Eulerian description, we have a field. We can describe different variables like pressure, density, or velocity with a field. And we can set a relationship between these two with this equation. So what are we gonna do? Well, in a study conducted by Baudena et al. In 2022, they found that there are certain zones in the Mediterranean Sea that cross a highest volume of plastic, and they call these crossroads. So they run the most principal crossroads in the Mediterranean Sea, but we only focus in one interesting point for us that is located at the north of Mallorca. Why this point? Because it's near to us and, well, maybe could some implication to the environment near to the island. So our principal objective is identify the principal zones where the microplastic come from and cross for this point. And how? Well, we have to assume some things like the particles that we are working on are floating particles, like goes to the surface of the ocean. Other thing that these particles don't interact with other particles, also with the water. And the particles are uniformly distributed over the sea. How we gonna do this? We getting data from Copernicus, the velocity fields, then interpolate the data with linear and bilinear interpolation, integrate the trajectories with a Ron-Yakuta method. Then when we found the final points of these trajectories, make a cluster with the K-means algorithm. And finally, the analysis of our data, our results. So what is Copernicus? Copernicus is a program created by the European Union that the main purpose is bring some information about the environment, real data. And well, how they do this with satellites. So they use satellite altimetry. That is a technique when the satellite sends a signal and measure the time that it took to return to the satellite, calculate the height, and then with these equations, we can calculate the velocity. Yes. So our data set, here are the schematic picture of our data set. So we have eastward and northward velocity are our data variables. And for the coordinates, we have depth, latitude, longitude, and time. So as we are working on the surface of the sea, we took the first layer of the depth, so at 3 meters. Latitude and longitude, we said like focus only in the Western Mediterranean Sea. And time, we took 4 years, these 4 years, and for each time we took 6 months, the equivalent to summer and winter for each year. What else? Oh, no. I don't know why. Okay. Well, here was the image of our dataset, the Western Sea with the eastward velocity plotting, but well, I'm gonna show you. Oh, no. So how do we compute the trajectories? Well, we interpolate our data and we solve with the Runge-Kutta method these two equations. So U and V represent the velocities that we took from our dataset, and R are the radius of the Earth. Well, phi the longitude and theta the latitude. So here in this picture, we took one statical velocity field on 1 day. It's from 1 day. And we went solve the equation, integrate the step plus 0.1. And well, the thing that we can see here is that the trajectory match with the velocity field. So here, well, we know that our Runge-Kutta works, so we have to integrate for 6 months. So we have to set our time step for 1 day. At the beginning, we set our time step of 1 day in this gift, you can say, and we integrate. So our time step is 1 day. We can see that the trajectory is not so smooth. So for the reason we want to like improve our trajectories for this time, we have to reduce the time step. To do this, well, we interpolate in time as well. And we calculate like the second gift when our time step is 1 hour. So here are the trajectories that we can find. And also we can see that the interpolating time and the one step of 1 hour is smoother the trajectory. Now that we have our trajectories, well, we need to integrate backward in time. So to do this, we set our initial condition near to the crossroad point. So we set our crossroad point, and around it, we set the initial grid, a square grid, and we put all the points in this grid. And then we integrate this backward in time. And well, this is an example. This is our range of initial conditions are integrated in one hour time step. And this is an example that crossroad 90 days backward in time. $90 Yeah, yes, it was only 90 days in that example. Well, when we have all the trajectories, we need to find the final point. So we find our final points of the trajectories and we plot it, like in this case. And then we need to determine the zones where this point belongs to a zone or other zone. So to do this, because there are not clear delimitation of the zones, we implemented the K-means algorithm, in which, well, it's a non-supervised learning algorithm, in which make groups with a characteristic that they have in common. It was a good approximation, but the only thing is that this algorithm needs to set appropriate number of clusters. And we find that an appropriate number of clusters was between 4 and 6, but in each case can change. For this reason, we have to look and change this number in each cluster for each time. Well, so the description of the trajectories. Well, this is our first results. We integrated 225 trajectories backward in time with the initial condition that I said before. in that years and in winter and summer. So as we first approximation, we can see that here in summer in 2013, we can see some anticyclonic circulation in the West Alboran Sea, like here. Also, for winter, we can see the strong Ligurian current that goes for all the coast until reach to the crossroad point. In 2015, also in summer, we can see some gyres in the front of the Leon Gulf, the strong Ligurian current. In winter, we can see some eddies in the Algeria Basin, as we can expect. In 2017, we have also cyclonic gyres in the Alboran Sea. In winter, also the Ligurian current and more dynamics in the Leon Gulf. And in 2019, well, like the same as we saw before, the more or less the same dynamics. So it's also worth noting that you can see that mostly the majority of the trajectories in summer comes from the South Alboran Sea and West Algeria. That, for example, in winter, that the majority of the trajectories comes from the north for the Ligurian Sea and Leon Gulf. Well, this slide is a summary of all of the results. We make the cluster, and these are the percentages for each zone. We identify 8 zones, mainly zones, the principal zones. And well, we split Algeria in 3 regions. So Algeria Basin was when the trajectory ends at in the sea, in the middle of the sea, in the basin. West of Algeria and east of Algeria were when the trajectory ends on the coast, in that part, but on the coast of Algeria. So in average, we can see that the most significant source of these particles was Algeria, all Algeria, the 3 parts, with an average of 30% of the trajectories. Also, we can find seasonality. Well, as we can see in the trajectories, we can expect some seasonality. Well, the main result was that Alboran Sea and west of Algeria contribute more in summer, like in 80%. Well, the predominant regions from winter are Ligurian Sea and Leon Gulf, as we can also see on the trajectories, with 47%, more or less. And if we average this percentage of all the time for all the times, we can see that the area that is more constantly is Alboran Sea with 21%, and then was with Algeria with 17%. The first 4 zones contribute like near over the 50% of all the contribution, the trajectories that cross for the north of Majorca. Also, we can see in the box plot that the distribution are not uniform, present also big variability. But well, this is due to the data. We don't have a big amount of data to put more statistics. And well, the zone that less contribute was Valencia, and also the coast of Valencia also was a little bit difficult to determine that part. So the conclusions are that we were able to identify the principal 8 zones, the microplastic that cross for Majorca. On average, we can see that Algeria is the most principal contribute more with 30% more or less. Well, we can find the seasonality as we can expect. There are more in summer predominant the south zones and in winter the north zones. And well, to implement or to do a better analysis or study, it would be a good idea do the same analysis, but taking into account more consideration, like don't start with the uniform initial distribution of microplastic, but start with some concentrated zones like coastal cities, rivers, that is more accurate. And like consider also that the particles can sink or interact, more interaction between them. Well, to conclude, it had been that this Lagrangian perspective can help to understand more about the dynamics of the ocean, the substance nutrients that can travel around this, try to understand more, and try to help our ocean and do something for the health of our environment. These are the conclusions and well, the bibliography, some of the bibliography. And thank you very much.
Thank you, Gon. So can you switch on the registers in the stop record. Abajo de todo hay un stop video. No, stop record. Bueno, stop. Stop recording.